All right, good. The next thing I want to take a look at over here is GRE. As I told you, encryption does, VPN does not require encryption. So I have the internet, I have one router. Let's just use the router over here as 199.111 public address. I have a network behind me. Let's say it is 10.1.1.0 and another network 10.1.2.0. And let's say I have a third network 172.16.1.0. I have another site, router 2, public address. It has multiple networks over here, 10.2.1, 10.2.2, and 172.16.2.0. I want to set up a VPN from R1 to R2. When I did the VPN over here based on IPsec, one of the drawbacks was the way I defined my interesting traffic. The interesting traffic was defined by using an ACL. Everybody agree? So right now I have defined that 10.1 traffic going towards 10.2 should be encrypted. This is my interesting traffic. Agree? Yeah. So this is the traffic right now that is getting sent across the network. What if tomorrow I decide that I also want 172.16 traffic to be sent to 172.16 as well as to this guy, and vice versa? So I want all traffic between these four sites to be able to talk to each other. What are my ACLs going to, what changes do I need to make to my ACLs? I need to add my existing one, looks like this, 10.1 to 10.2. Over here, it would be 10.2 to 10.1. Agreed? That's my existing one, right? Now that I have a requirement of adding a new network to this VPN tunnel, I need to accommodate that by allowing 10.1 also to send traffic to 172.16.2.0. I want 172.16.1.0 to be able to go to 10.2.2.0. I need to allow 172.16.1.0 to go to 172.16.2.0. Not only that, I also need to do the same thing on where? The reflexive ACLs on the mirrored ACLs on the other side. You guys agree? It's like creating static routes. What you're doing right now is something known as a policy, which is an ACL based VPN. Okay? All good? Yeah? The drawback of this is it's static in nature. Why is it static in nature? Because of the policy. Anytime a new network needs to be added, I need to define the policy on both sides, A to B as well as B to A. Understood, guys? Now, the alternative to that would be, rather than doing static routes, why didn't I run a routing protocol between R1 and R2, and in that routing protocol define what traffic needs to be encrypted? with IPsec. The reason is, I'll get rid of this. The reason is, in order to run a routing protocol between the two sites, not multicast, Mike, I'll explain that. In order to run routing protocol between router 1 and router 2, they need to be directly connected to each other. And the way I established the tunnel over here was not based on an interface, I did it based on a policy. So I would look at the traffic and based on that encapsulate it. Okay? If I could technically create a logical interface that simulates as if R1 and R2 are connected to each other, then I would be able to run a routing protocol. So the requirement of the routing protocol to run is that R1 and R2 logically should be connected to each other. And that's exactly what a tunnel interface provides us the capability of doing. What is a tunnel interface? It's a logical interface which will have a tunnel source and tunnel destination, public addresses. So any packet that goes through the tunnel will be encapsulated with the tunnel source, which will be the public address, the tunnel destination encapsulated. And inside there will be the data. But the thing is, it will be done based on a tunnel interface, an interface that encapsulates. The tunnel network itself will be given an IP address. I'm going to give it an IP address of 192.168.1.0, this being .1 on that network, this being .2 on the network. So logically, I'm connecting them as if they're directly connected using this virtual interface called the tunnel interface. And the protocol that is run on the tunnel interface is a protocol by the name of GRE. The encapsulation of the outer header to the inner header is done based on a protocol called GRE. So let me just bring up that diagram for you. So to run a routing protocol between two routers, they need to be directly connected to each other. If you want to do it on the internet, you can create a logical interface known as a tunnel interface. The tunnel interface will encapsulate the inner header to the specified destination. This connects the two endpoints to each other as if they're directly connected. The protocol that you're going to be running is GRE. So this is the diagram. This is the way the diagram will look. As if this guy and this guy are connected to each other physically, which is logically actually, using this common network. So now, logically, R1 and R2 will be looking like this. Now I can run a routing protocol because now I have a common network between the two routers. Good so far, guys? Understood. So what I'll do is, I will go back over here. I'll stop this topology. I don't need this. Instead, I'll open my topology again, the same one that I had. Start it up. Let's go to 1, 2, and 3. The diagram looks like this. Same diagram. But now what I'm going to do is logically connect up R1 and R2 to each other over this tunnel interface. This tunnel interface will simulate as if they're directly connected. Everybody following along? Okay. This is your GRE. So how do I do that? Over here, router 1. We're not talking about encryption at this point. Just a VPN. It is a VPN because it's connecting two private to each other. It's not encrypted VPN, but it's still a VPN. So show IP route. Right now, it shows me the two LAN segments. It has a default gateway towards the ISP, and this is my public network, 199. Router 2, the other side, basically the same thing, two private networks, and then the public network and a default gateway. So to create the tunnel interface, very simple. This is going to be lab number 4 for us. Configure a LAN to LAN, GRE VPN to connect R1 and R2 to each other using a tunnel interface. Set the tunnel network to 192.168.1.0. Run EIGRP in AS111 to route the LAN segments over the tunnel network. Now I can run a routing protocol because router 1 and router 2 are directly connected to each other. So the way I do that, configure the tunnel interface. Interface tunnel, any number locally significant. IP address that I want this tunnel interface to have, 192.168, I'll call router 1.1. The tunnel source, any packet that goes over the tunnel will have this as the outer head, my public address. And the destination, the public address of my other peer. This is a point-to-point tunnel, so it's only going to have one point, one destination. This is on R1, and I would do the same thing where? On R2. The difference, the address over here on the same network, a different IP. He's .1, I'm .2. The tunnel source. Now I could do this, or if you want, you can just say pick the IP address from this physical interface. The source could either be specified, or you can pick it up from the physical interface. And the destination is 199.111. Understood, guys? You guys are okay with this? And that would basically make the logical network as if I have router 1, router 2 directly connected to each other over this tunnel network and has some public, private networks, I can route it. Any traffic that goes over the tunnel network will automatically be encapsulated. Encapsulated, not encrypted. All right, go to router 1. How many interfaces do I have right now? I have two loopbacks, the two LAN segments and the public network. As soon as I create the tunnel interface, I have a new directly connected interface, which is called tunnel network. If I look at the tunnel network itself, it tells me this IP address of this tunnel is 192.168.1.1. Any packet that goes over the tunnel will be encapsulated, and the source will be 199.111. Destination will be 200.111. You guys following along? And the protocol that it's using is GRE. That's the default protocol on the tunnel network. Okay, this, by the way, is GRE. Point to point. Understood, guys? Everybody following along? Yeah? Simple? Quick? The default protocol is GRE, yes. The tunnel interface, when you create it, the default protocol is GRE. So I'll copy this over here and do the same thing on R2. Now again, if I check my routing table, shows me 200 as the public, and then it shows me these directly connected interfaces, including the tunnel. On R1, same thing. These are my networks, and this is my public interface. Now let's take a look at a packet. Let's say I'm sitting on R1 and I want to ping R2 over the tunnel. Now, logically speaking, I'm looking at it like this. Okay, dot one and dot two. So if I sit on R1 and I say ping 192.168.1.2, it goes and checks the routing table and which entry in the routing table does it match. If I'm trying to ping 192.168.1.2, help me out. Which routing table entry does it match? This guy, right? Says, okay, that becomes my tunnel, the packet source address. So this is what the packet will look like. 192.168. Pick the source IP over here. Destination 192.168.1.2 because that's what I'm pinging. Now it says it's directly connected. See the C over the tunnel 1 network. Now it goes and checks the tunnel. And what does it see in the tunnel? In the tunnel, it sees, so now that it's matched the routing entries, in the tunnel, it sees that it is a GRE tunnel, and the tunnel source and destination is this guy. Creates a packet, encapsulates it automatically. It automatically knows the GRE interface needs to be encapsulated. This is your GRE packet. And this is, let's say I was doing a ping. This is the inner packet, which in our case over here is IC. And sends it across. Let's check. And the other thing that I'll do over here is enable a Wireshark capture. So we can see the packet as well. Okay, nothing going on right now. Let's go and ping 192.168.1.2. I'm on R1. I'll send the ping. Let's check. Check the first packet over here. The packet has an outer header. Source address of 199. Destination address of 200 using GRE. The inner header is right here. And just in case you were wondering what the data looks like in a GRE packet, this is right here. Not GRE packet, sorry, a ping. This is what a ping packet has as data. Just in case you're wondering, 72 bytes of crap. Good so far? Everybody okay with that? Now, although that's the case, can I, at this point, reach the 10.2 network or 10.2.2 network over here? I can't. Why not? My routing table has no idea about the networks behind R2 because I haven't run any routing protocol. So I need to run a routing protocol over this directly connected network between R1 and R2 to learn the routes on the other side. So tomorrow, if a new network comes up, all you got to do is advertise that network in the routing table, and the fact the route gets advertised. So the next thing is to run my routing protocol. So how do I do it? Configure the routing protocol on the tunnel network, tunnel interface, and the internal LAN segments. Don't run it on the public. You're not running it with the ISP. So I'll say router EIGRP 111 network. My tunnel network and my internal networks both are 10. So I can just say 10.0.0.0 and do the same thing for the other side. So now I'm simulating as if R1 and R2 are directly connected through that tunnel network, and I'm enabling EIGRP on it. So let's do it on R1, and I'll do it on R2. And by doing this, what's going to happen is EIGRP will form a neighbor relationship over the tunnel network, tunnel interface. Good. Not only that, I would have learned the routes to the tunnel interface. Now, what happens? If I say ping, now that I learned the network 10.2.1.1, let's say from a source of 10.1.1.1, as an example, it goes and checks the routing table. In the routing table, this address matches 10.2.1 over here. It creates a packet. Source I've specified, so the packet looks like this. I'm on 1, so the source is 10.1.1.1. Destination is 10.2.1.1. Okay. Now it says go through the tunnel. What did I tell you? Any packet going through the tunnel, what does it do? Any packet leaving the tunnel, it knows to encapsulate it to the tunnel source of 199. As long as my routing protocol says go through the tunnel, or routing table says go through the tunnel, it takes that packet and encapsulates it with GRE. The inner packet is ICMP. Good. It should now work. So now I have set up my VPN using GRE. Let's just make sure that I can't ping it. 10.2.1.1, source 10.1.1.1. There you go. The ping is successful. If you go take a look at the packet over here, you can see that. This is the ping that I just sent. Public address is always going to be the 199 and 200. And the source is 10.1 to 10.2. This is that ping that I just sent. You guys okay with this? So this brings that dynamic nature into the picture. Now, let's say a new network comes up. Let's say, hypothetically speaking, a new department has come about in the company, and I've added a new network over here, 172.16.1.0. All I got to do is introduce this network into what? My routing protocol, and the other guys know about it, just like a dynamic network rather than a static network. So let's do that. Let's simulate that. I'll go on to router 1 and say, oh, new network came up. I'll create a loopback. Loopback 1, so I'll create a loopback 2. 172.16.1.1. And go into my EIGRP and advertise it. Done. As soon as I do that, the routing update will go across over here, show IP route EIGRP. 172 is over here. So I don't need to do anything on this side. As long as he advertises it, now I should be able to read it. There you go. So the dynamic part that was missing in IPsec LAN to LAN now is there. There, guys. This is GRE VPN. So these are the steps. Once the tunnel is established, now you can run a routing protocol over it, which we did over here. You will learn the peer network through the tunnel network. I showed you the show IP route statement. It'll show up in your routing table with the next hop being the remote. Here's tunnel IP. Let me just make sure you guys can see that as well. So I'm learning 10.1 via the tunnel IP of the peer, 192.168.1.1. How did you tie the protocol to the routing protocol? The tunnel interface, you mean? When I ran my routing protocol, I ran it on the network 192.168.1.0. So it basically searches the routing table and sees which interface is 192.168.1.0. So it enables the EIGRP on it, which happens to be my tunnel. Good so far, guys? Now that we have done that, this is what the packet looks like as a sample packet. And I'll show you that in my Wireshark as well. These are your hello packets right now. I want you guys to take a look at the size because I'm going to use this as a baseline. Because when I encrypt this packet, I won't be able to show you the inside of the packet. So we'll use the header as a sort of a validation. What is the size of this EIGRP hello packet? This is an EIGRP hello that I just showed you. The size is 98 bytes. How do I know it's an EIGRP hello? Besides, this is the outside. That's okay. It is source of 192.168.1.1 on the inside, 224.0.0.10, which is EIGRP. But now how do I know it's a hello packet besides the header over here? If you open this packet up, this is what an EIGRP hello packet looks like. Again, it's clear text, but it's getting propagated across. This is my AS number that I used. What's the size? 98 byte size, and that's what I'm showing you over here. Overall, everybody understand this packet? It's a GRE packet, outer header, public addresses, inner header is my GRE, EIGRP packet. In my case, the address is 1. Yeah? GRE good? What's the drawback of this? Although I did take care of the dynamic part of the IPsec drawback, the problem is this is all clear text. I showed you the packets. I showed you your ping packet. I showed you an EIGRP hello packet. Everything is in the clear. Yes, it's encapsulated, but I can see this data. There's a difference between encapsulation and encryption. Yes, I'm encapsulating it. Encapsulating means what? Putting one packet within another packet. I am doing that, and I showed you that, but I'm not encrypting it. It's clear text, so you can actually see the packet. Clear? The interface has no issue with multicast. The tunnel interface has no issue with multicast. So when you enable EIGRP on the tunnel interface, it'll send any packet. So once the packet is set on the tunnel interface, it knows it needs to encapsulate. Got it, Trent? So the drawback of this is that it is clear text. So what they say